Today, we're going to look at some exponential decay, and it's going to be a really natural add-on to the exponential growth we saw yesterday. So you're going to see a lot of similarities and hopefully tie a lot of things together. And I'm extra motivated to dive into this topic today because, sometimes honestly, math can be a little bit of a drag when you don't see that connection with how this could affect everyday life. But I think in this type of topic, you're starting to get an idea of just how many things in our everyday lives can be modeled with exponential functions. So yesterday we got into this general form. And we talked about how, yesterday we used y equals a times b to the x. And today I'm just using f of x, but it's the same thing. And we defined a as the initial amount of, whatever's the topic in the context. And b is going to be defined as either, yesterday it was just 1 plus r. Today it's going to be 1 minus r. And we're going to be focusing on the decay model, okay? But there was three conditions that had to be met to be exponential. First of all, the variable had to be in the exponent, okay? And then we also said the coefficient a, that leading coefficient, cannot be 0. And then the constant b, b had to be positive, and it couldn't be equal to 1. Okay. And so, but we're going to really focus on that b value today. That b value is going to give us some insight as to whether the function's growing or decaying. So how do we tell the difference between growth and decay? Well, if that base value is greater than 1, it's going to be exponential growth. So that's everything we saw in yesterday's video. And today, that b value is going to fall somewhere between 0 and 1. So it's still going to be positive, but it's going to be less than 1. And now we have exponential decay. And a lot of these are really straightforward, and then we'll show you a couple of bear traps. So if we're talking about exponential growth, I'm envisioning the function 1 plus r. So I'm just replacing that b value that we had up here in the parentheses. I'm just replacing it with a 1 plus r to emphasize growth. But if it was decay, now I'm going to replace it with 1 minus r raised to that x power. So here's just a couple of examples to kind of get ourselves in the right frame of mind. This first example, you always want to go from left to right. So as you move from left to right, we're falling. So this is a decay problem. Probably not the best idea to write with my highlighter. Again, if we go from left to right, this graph is also falling as well. So we'll say decay. Now this next problem is rising, right? Going up. So we've got ourselves a growth model. And again, going from left to right, we're rising, going up, 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 up. So we got ourselves another growth model. Notice sometimes they're above the x-axis, sometimes they're below, sometimes they intersect. But we're just worried about whether they're going up or down. Okay, so let's try our luck at interpreting some equations here. Now, one thing we want to really focus on is making sure this exponent's positive. As long as that exponent's positive, the problems are very, very, very simple, okay? So in this first one, focus on your b value. So if your b equals 1.89, anything bigger than 1 means we're growing, right? So we're growing, or we've got growth. In this case, it would be at a rate of 89% each year, assuming x is years. All right, next one, we've got ourselves a positive exponent. That's great. And in fact, let's see here. So I've got a b value of 0.92. That's less than 1. And so now we are decaying. And what we're going to find out is this is a rate of 8%. In other words, what did you subtract from 1 to get that 0.92? So sometimes what you could do is if you're doing scrap work off to the side, you could say, if we know that b equals 1 minus r, and in other words, 0.92 equals 1 minus r, when you solve for r, you're going to get 0.08 and then move the decimal twice to get that 8%. Okay, we've got ourselves a positive exponent, which is good. So our b value is a 0.8. Anything less than 1 means we're decaying. And in this case, we're decaying at a rate of 20% every 3, whatever, if it's years or months or days, whatever the units are there. And similar in the next one here, let's see, we've got a base value of 2.13. Anything bigger than 1 means we're growing. So we've got ourselves some growth. At this case, it would be 113% every 4 years. Now you're saying, whoa, 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 time out, Hill, time out, Hill. How did you get 113%? Well, remember, if we're talking about growth, our B is equal to 1 plus R. So we could take our 2.13, set it equal to 1 plus R, and R equals 1.13, and then you move that decimal place twice to get 113%. Okay, so here comes the really advanced bear traps here. Notice how we've got a negative exponent in the next two problems. So what I'm going to do is I'm going to manipulate and rewrite these functions. All right, so imagine writing 0.68 as a fraction. Think of it as 68 over 100. Remember how we said a couple of videos ago, if we have a negative exponent, we're going to reciprocate that base? And that's going to make the exponent positive. So like on the surface, this might have looked like a decay problem, right? At first glance. But once you manipulate it and rewrite it, I'm going to grab my calculator. 100 divided by 68 makes 1.47. So if I rewrite that function, I've got 1.47 raised to the x. In other words, we're growing at a rate of 47% each year. 7. Okay. Same thing on the next one. The next one's very deceiving. You see the 1.24 and you're automatically thinking growth, but not so fast, my friend. When you see 1.24, picture that as 124 over 100. Okay. And then we're just going to rewrite the function. We got 18. We're going to reciprocate it. So the 100's on top. 124 is on the bottom. Now it's raised to the positive x. And if I go 100 divided by 124 on my calculator, I'm going to round it to 3 decimals, or I might as well just go 2 decimals because that's even easier. We'll go 0.81. So that 0.81 is less than 1, so we're decaying. And if I subtract 0.81 from 1, I'll get about 19% each year. So those last two are extra, tricky ones to watch out for. Let's take a look at writing some exponential equations and just interpreting some scenarios we could run into. So right out of the gate, Tom's got a cattle ranch in Texas where he's got 2,400 longhorn cattle. Sounds like a good life. And that herd size is increasing at a rate of 4% every 2 years. So the moment that I read increasing, okay, and we've got our percentage involved. So literally that percent is what tells you we're exponential. And increasing means we're using the function a quantity 1 plus r. So this is a growth problem. And we'll just put an x or a t up there. So I'm going to use the function. We'll start off with 2,400. We're going to go 1 plus 0.04 as we convert the percentage into a decimal. And since it's every 2 years, we'll just do x divided by 2 to take into account that frequency. All right, next example here. Last January, there was 150,000 travelers that flew through the Buffalo airport. However, COVID hits and the number had decreased by 83% per month since the pandemic. So our time is measured in months, okay? And we could simply say, and it's decreasing, right? It's decreasing. So the function I'm anticipating here is 1 minus r. And so in this particular case, we'll use 150 and it's already measured in thousands. And we'll do 1 minus 0.83. And it's just per month, so we could just do x. We don't have to divide it by anything. And if we did clean that up just a smidge, we'd get about 0.17 raised to the x. All right, let's go Buffalo. We initially had 50,000 fans at the beginning of the season. And since that start, the number of fans has doubled every month since the start of the season. All right. So you may remember seeing that phrase doubling from last night's video. In other words, what that means is we're increasing at a rate of 100%. That's what it means to double something. So we're increasing at a rate of 100%. So let's say the amount of fans is going to be 50,000 and it's doubling. So you could do 1 plus 1.00. Oops, I keep go t's, but I've been using x's, so I'll just try to be consistent there. And that's just going to make a base of 2. So anytime you have a base of 2, we're doubling. In the year 2000, there were 720 polar bears in the world. Since then, the number has decreased. Let's highlight the word decrease at a rate of 6% every 2 years. Go ahead and try to write your own function here. Great time to hit pause and test your luck. 720 polar bears. We're going to go 1 minus 0.06, and then we'll go x divided by 2 for every 2 years. All right. I know the price of houses, especially in the village, has just skyrocketed recently. So let's pretend that they initially bought their house for $210,000 in the year 2010. Since then, the value has increased at a rate of 8% every 3 years. So let's say the value of their house will go $210,000, 1 plus 0.08, and that's raised to the x divided by 3. All right, last one, definitely a very advanced one here to finish things up with. There initially was 500 grams of some radioactive material, and it has a half-life of 5,700 years. Now, the way we interpret a half-life is I want you to think about it like this. The amount of material is decreasing at a rate of 50%, and in this case, every 5,700 years. So let's see how we're going to rewrite that. The amount of material is equal to 500 times 1 minus 0.50, because it's decreasing by 50% every, keep wanting to say t. Maybe I should have just gone with a t. I've been fighting it. My habits have been fighting me there. And so that's x divided by 5,700, because that's how long it took to decay 50%. All right, should we test our luck at graphing? So very similar to yesterday, we're just going to start off with a t-chart or a table of values. And my philosophy is always the more the merrier, especially when you're first learning a new type of function and how it behaves. So we'll go from -4 to 4. And you could always type this function into your calculator to generate that table of values. This one might be just friendly enough that you feel confident evaluating these in your head. But we are expecting a decaying or decreasing type of model because our base is less than 1. And so we'll get a 16 and an 8 and a 4 and a 2 and a 1. And let's go 1/2, 1/4, 1/8, 1/16. And we may convert these to decimals. So we've got a 0.5, we've got a 0.25, we've got a 0.125, and a 0.0625. And we'll graph those as carefully as we can. So I'm going to start way up here. In fact, I'm going to just switch up the pen color for fun, make it look a little more exciting. And then at -3, we've got ourselves an 8. So it's really dropping very fast right here. -1, 2, 0, 1. And then it starts to kind of level off. And this is where it gets really tough to graph it. And we just kind of do the very best that we can. And we'll connect these dots. So our function is decreasing at a decreasing rate as it starts to level off. Try to be very, very careful. We're getting closer to the x-axis, but we don't actually touch the x-axis, and that's where this asymptote comes into play. So we'd say just like yesterday, there's a horizontal asymptote at y equals 0 right along the x-axis. So our asymptote is y equals 0, or the x-axis. And the domain, it does extend infinitely to the left and infinitely to the right. So our domain is the set of all real numbers. The range is going to be everything above 0. So not including 0 because it doesn't touch the x-axis. So from 0 up to infinity. Last thing we're going to dive into, again, is just working with these word problems. The number of home runs allowed by the New York Yankees pitching staff in the season is modeled by this exponential function right here. What a great looking function. Okay. Where t is measured is the number of years since 2010. How many home runs were allowed during the 2010 season? That's going to be your initial amount, which is going to be your leading coefficient. So we said 190 home runs allowed in 2010. Is the number of home runs increasing or decreasing? Well, we do have a big bear trap here. On the surface, it looks like the number of home runs is increasing because you see a 1.05, but notice the negative exponent. So that's going to force us to have to try to rewrite this function. Now, 1.05 is 105 over 100. And then what I'm going to do is I am going to take the reciprocal. So the 100's on top, the 105's on the bottom, and now my exponent's positive. And maybe we'll just express that as a decimal. since it's easier to do as a decimal, 100 divided by 105. And I'm going to round this to 2 decimal places for convenience sake. So we've got 0.95 raised to the t. So I'm actually going to say the number of home runs is decreasing at a rate of 5% per season or per year. How did I get 5%? Well, we're going to take our base. Remember that we said base is equal to 1 minus r? So if I took 0.95 and set it equal to 1 minus r is going to equal 1 minus 0.95, or in other words, 0.05, and then move the decimal place twice. How many home runs would you expect their pitching staff to allow during the 2010 or 21 season? Well, that is going to tell us that's 11 years since 2010. So we're going to substitute an 11, and we'll say h of 11 is 190, and you could use any of those functions. I'm just going to go back to the original function to be safe. That way, in case I did make a careless mistake somewhere in that process in part B, that mistake won't cost me this answer right here. And we'll just evaluate this on our calculator. So we're typing in 190 parenthesis 1.05 raised to the negative 11th power. And wow, pitching staff, whoever their pitching coach is, he should get a bonus because they're doing a great job. That's only about 111 home runs allowed for the entire season. So that's less than 1 home run per game because they play about 162 games. So someone's doing their job there. All right, ladies and gentlemen, hopefully you feel pretty good, and we'll see you tomorrow.